Welcome everybody. Today we're going to cover and start learning about the hydrocarbons. The hydrocarbons are compounds that are consist of hydrogen and carbon only. Okay? And the hydrocarbons are separated to two type of families, the family of alkanes and the alkenes. The alkanes are organic compounds with the general formula, which is CnH2n plus 2. And this is for straight chains. Straight chains. Like what? Like CH3, for example, CH2, CH3. As we can see, this is a chain that is composed of 3 carbons. Okay, so if we apply the rule, it will give us C3H. 3 multiplied by 2 plus 2 equals 8. Then we're supposed to have 8 hydrogens. We have 3 here, and 3 here, and 2 here. So this is the general formula, and this is alkane. Okay. Another thing to put in your mind, you have another form of alkane, which is cycloalkane. The cycloalkane looks like a cycle. Okay, like this, for example, but they have a general formula of CnH2n. And the reason behind, because 2 hydrogen are missing from the 2 terms of the straight chain when you make a cycle like this. So this is the general formula of cycloalkanes. What makes alkanes unique and different is they are unreactive. And if you ask yourself why they are unreactive, we have 2 reasons behind. Reason number 1, because these compounds are considered non-polar, and there is a relationship between the polarity and reactivity. The polar compounds are reactive. So, as we can see, this is on non-polar, and the reason because they are non-polar, because they have a small electronegativity in CH bond. The small difference in electronegativity makes them nonpolar, and that's why they're unreactive. We have another reason, which is the CH bond is considered as a strong bond. The strong bond means that you need a lot of energy to make a reaction, and that's why this is one of the reasons. So we have 2 reasons for their unreactivity, because they're nonpolar due to the small difference in electronegativity and due to the strength of the CH bond. Okay. Let's go to the family of alkenes. The family of alkenes. The alkenes have a general formula, which is CnH2n. And it's the same as the general formula of cycloalkanes. But we have a difference in this case because they have a double bond. And once they have a double bond, we can conclude that they are more reactive due to the presence of the double bond. The double bond contains high electron density in this area, which is the double bond, and that's why it's prone to make reactions in this case. How can I distinguish between alkane and alkene? For example, in this case, if you have cycloalkanes and cycloalkenes. If you add bromine, for example, Br2, and it must be in aqueous form, to both materials, the bromine aqueous solution will react with alkene because it's more reactive, and you will get observations. But if you react it with alkanes, no reaction will take place in this case. So we have 2 hydrocarbons, we have alkanes, alkenes. The alkenes are more reactive due to the presence of the double bond. Do alkanes make reaction? The answer is yes, they make reactions. But the only reactions that alkane can make are combustion reaction and the free radical substitution. Let's go to the combustion reaction. As you can see, the combustion here is separated to 2 types. We have complete combustion, okay, and we have incomplete combustion as well. But if you ask yourself what is the difference between these 2 types or these 2 combustions, the only difference is when you have complete combustion, it means you have a lot of oxygen gas, which means like suppose that we have this alkane, which is methane, You react this methane with oxygen, and in this case, the oxygen is in a great amount, okay, and it gives carbon dioxide and water. These are the normal combustion products from any organic material, as we can see. So in this case, we just noticed that we have methane with a lot of oxygen produces carbon dioxide, okay? If you have incomplete combustion, then the reaction will be like CH4 plus O2 gives CO plus H2O. So this is the only difference. We have small amount of oxygen that reacts with this methane or this alkane. The product in this case is carbon monoxide. And you just notice that carbon monoxide is a carbon, it's an oxide of carbon with one oxygen. But here you have two oxygens. When you have two oxygens, as we can see, it means that you have a lot of oxygens. But if you have lack of oxygen, then the product will be carbon monoxide. And by the way, carbon monoxide is toxic. And it has no smell, it has no color, and that's why it has a great effect on the lungs, especially when it's bind to hemoglobin instead of oxygen. And that's why sometimes it's called silent killer. But for carbon dioxide, it's considered as a greenhouse gas, and it enhances the global warming as well. But carbon monoxide is worse than carbon dioxide. All right, so now we have the difference. We learned the difference between the complete combustion and incomplete. When you have incomplete combustion, then the production of carbon monoxide will be happen here. And if you have carbon dioxide, then it's a complete combustion in this case. All right. So put in your mind, you're talking about the reaction of alkanes, which are, let's say, hard to react. And if you want to make them react, you can put them under harsh conditions like combustion. You're burning them. So yeah, this is harsh condition. And now let's go to the second type of reactions, which is the free radical substitution. It's used to make halogen alkane, like for example, like CH3, Cl2, for example. This is alkane that is bonded to chlorine, or let's say halogen. What you should know about this free radical, we're going to learn about how to make reaction between bromine and alkane and Cl2 with alkane. The free radical substitution takes place in steps. The step number one is the initiation process. The initiation indicates that you have the halogen, which could be Cl2 or Br2. So let's take an example like Cl2. In this case, we're going to apply the UV light. The UV light is a certain type of radiation that it presents in the sunlight. So sometimes you can write that like on the arrow, like the condition of sunlight or the UV light, it's okay, both are correct. The sunlight or the UV light gives energy to the chlorine molecule in here. And as a result of this energy that will hit this bond, this will be a homolytic cleavage. And that's why the product here will be chlorine radical. And we represent the radical by this dot, as we can see. Let's recall the definition of the radical. The radical, it's a molecule or atom with paired electrons. So as we can see here, the chlorine contains 7 electrons in its outer shell, and this is odd number. And that's why we can consider it as a radical. The radicals are very reactive species. Okay, these are very reactive species. And put in your mind, the first step in here is endothermic. This is endothermic process. This is endothermic, and that's why you need energy. The source of energy, it could be sunlight or UV. Okay, so this is a radical. Okay. We're done with the initiation process, and now the reaction starts. So the next step will be propagation step. What you should put in your mind, the propagation step is exothermic. It's exothermic, which means it gives out energy. And let's describe it in terms of equation. And now let's have a CH4, for example. We're going to make a reaction between alkane and this highly reactive species, which is Cl radical. According to what you have here, the mission of this radical, which is very reactive, it will hit and catch. Okay, it will hit the methane molecule. Okay, and there will be a homolytic cleavage as well. Here we have hydrogens. You just notice that once this Cl radical hit this bond here, a homolytic cleavage will take place. And the product in this case will be CH3. And here we have a radical because we have a bond that is broken. And this Cl chlorine radical will catch one hydrogen. And then the product here will be HCl. So as we can see in this product, and here as we can see, the chlorine radical changed to a molecule. The molecule changed to a radical. And this is the propagation, as we can see. All right. Put in your mind, we have another very reactive species is produced in here, which is the CH3. And now CH3 can attack another molecule. And this molecule in this case is Cl2. Put in your mind, not all of the chlorine molecules change to radicals. Some of them remain molecules, okay? So in this case, what is the mission of this radical? It can hit and catch, and that's why you will get CH3, Cl, and this will change to radical here, and we have a radical. Okay, we still have another thing to be discussed in this case. This propagation step is called chain reaction, which means like once this reaction starts, it will start like hitting the molecules together with radicals and producing more radicals and more molecules, more radicals and more molecules until one of the reactants used up. Then we will start the termination process. So we're going to complete this reaction. So this is a molecule in here. This molecule can react like CH3, Cl. It reacts with chlorine radical. We just noticed that the radical can hit and catch. So it will hit this molecule in here, forming CH2Cl radical, and we got HCl. Okay, so we just noticed that we have another radical, and this radical can react again with another Cl2 molecule, like CH2Cl reacts with Cl2, and it will give us CH2Cl2 plus Cl negative. And just notice that it will be continuous process. I want to erase the termination in here so I can write the possible products in this case. Okay, I want to just revise, just get rid of this. Okay, and now let's complete it again. So here we have another good molecule like CH2, Cl2. It must be broken by a radical. This radical is a chlorine, as you can see. Then the chlorine radical can hit and catch, CHCl2, and we have a radical plus HCl. This radical is highly reactive. Then this highly reactive radical will react with another chlorine molecule, Cl2. Okay, just remember that the radical can hit and catch, and then it will hit this chlorine, catching one of them and producing another radical like CH3 plus Cl, and this is a radical. All right, so this is a molecule. It will hit a radical like, just use another color. Here we have CH3. It reacts with a radical, and the radical can hit and catch, forming CCl3, and this is a radical plus HCl. This radical again will hit another chlorine molecule, Cl3 plus Cl2 gives CCl4 plus Cl radical, and you just notice that we ended up in here. As we can see, this process, which is the free radical substitution. This is the free radical substitution. One of the limitations that you're getting different mixtures of materials, like you have a mixture of dichloro, tetrachloro. We have these products like CH3Cl, we got CH2Cl2, we have CHCl3, and we have CCl4. By the way, producing these chlorinated compounds depends on the amount of chlorine in the process. And one of the limitations, or let's say this process is not good, or let's say it's not that practically good in industry because it gives you different mixtures. Let's go to the last one, which is termination process. The termination process takes place once you have consumption, or let's say one of these reactants is consumed, and that's why it's time to end up the reaction. So the termination indicates the reaction between the two radicals. So we could have this reaction like with CH3, so we can have CH3 Cl, or you could have these two radicals like CH3 and CH3, and you could have this one like CH2 H6. So these are the termination. The termination indicates the reaction between radicals, but the propagation indicates the reaction between radical and molecule. Okay, just notice that here. You have radical and molecule, radical and molecule, radical and molecule, etc. And that's it. Yeah, that's it.